Okay, so I've got another question from gravitational fields. It says the escape velocity is the minimum speed needed for an object to escape from the gravitational field of a planet, and that an object traveling at the escape velocity has the kinetic energy equal to the magnitude of the potential energy at the surface of the planet. So for an object to escape the gravitational field of a planet, it needs to have the kinetic energy equals to the potential energy. And they've specifically told us the magnitude of the potential energy, so we're going to put a modulus here on it. So kinetic energy is equals to potential energy. Okay, so that's what we have to do here, and we have to derive an equation for this escape velocity v at which this planet that has this let's say satellite orbiting will escape. Okay, so let's find that out. We have let me change my pen here. We have the kinetic energy is equals to the gravitational potential energy. Kinetic energy is going to be half mv squared. Gravitational potential energy is gmm over r squared. And then what we're going to do is, not r squared, my bad, r. And then what we're going to do is we're going to move the 2 to the other side. The mass will cancel out, so v squared is equals to 2 gm over r, and then v is equals to square root 2 gm over r. Okay, so now that's the first part, very easy for 2 marks. Then we need to find this. Show that the escape velocity for a mass at Earth's surface, so something that is at Earth's surface, so this is Earth. So if something is on the surface of Earth, what velocity would it need to leave the surface of Earth? So we can find that out. V is equals to square root 2 times 6.67 times 10 to the raised power of minus 11 times 5.98 times 10 to the raised power of 24 over 6.36 times 10 to the raised power of 6. So let's quickly find that out. So that's going to be 1.19 times 10 to the raised power of 3, actually it's going to be 4 meter per second. Actually 119, okay? 119 times 10 to the power of 4 meter per second, that's approximately equals to 1.1 times 10 to the power of 4 meter per second. And hence we have showed that this is the escape velocity of the any object on Earth's surface. Okay. Now the next part is actually connected to the entire question. It says, when the Earth formed, a large proportion of the gas in Earth's atmosphere was hydrogen. Explain why hydrogen gas is no longer a large proportion of the gas in the Earth's atmosphere. No further calculation is necessary. So the first thing you have to understand is that the root mean square velocity is an average value or a mean value, but the way we calculate this value is a bit different. We add v1 square plus v2 square plus v3 square over 3, and then we square root it. So we do this for everything, and then we get our root mean square velocity. Right? That's what we do. Now we have to understand that some hydrogens can be traveling faster than the root mean square velocity, and some can be traveling slower. So that's the first thing you have to understand. Now, out of these hydrogens, it is possible that a lot of these hydrogens had enough velocity, or their velocity was greater than the escape velocity of Earth. Right? So these hydrogen atoms that escaped had a velocity greater than the escape velocity, and hence we can say that a large proportion that escaped were actually the hydrogens that had the velocity greater than the escape velocity of Earth. So that's basically the answer, and we have to really connect this with the previous parts as well. So I hope you get the idea of what's going on. Okay, then we have another question here as well. This is question on gravitational fields. It says the Earth is 9.3 times more massive than Mars. So the mass, I can say the mass of Earth is 9.3 the mass of Mars. And then it says the gravitational fields of Earth is 2.6 times greater than the gravitational fields of Mars. Okay, and then we have been given the mean radius of Earth. So what we can do here is, and then we're told to find the mean radius of Mars. So we have been given two things there about the mass and the gravitational field comparison of Earth and Mars. So I've written that down here for you. And then we need to calculate the radius of Mars. So we know the gravitational field formula is gm over r squared. So what I'm going to do now is I'm going to write down some things here. So first I'm going to write the gravitational field of Mars is equals to the g constant times the mass of Mars divided by the radius square. And then we're going to write the gravitational field of Earth is equals to g, the mass of Earth, and the radius square of Earth. Okay. Now, what I'm going to do is I'm going to take both of these equations and I'm going to divide both the equations. So I'm going to take both the equations, I'm going to divide both the equations. Okay. Now, as soon as I'm going to divide these equations, I have to realize the g cancels out. And then I'm going to get gm ge is equals to the radius square of Earth times the mass of Mars over the mass of Earth times the radius square of Mars. Now what I know is that GE is basically 2.6 GM. So I can write here GM and then 2.6 GM instead of GE. The gravitational field of Earth is 2.6 times the gravitational field of Mars, so I've just replaced it with that. And I know the radius of Earth is given, square, times, now I know the, so this is the mass of Mars, and now I know, okay, and then we know the mass of Earth is 9.3 times the mass of Mars and radius m squared. And this one cancel out, and this one cancel out here, and I'm going to be left with 1 over 2.6 is equals to the radius of Earth square over 9.3 radius of Mars square. If I move things around, I'm going to be ending up with this equation, and if I square root both sides, I'm going to find the radius of Mars. So I've plugged in all the values, and now let's find the radius of Mars. That's going to give me 3.368 times 10 to the raised power of 6 meters.